Welcome. Today, we're going to decode the invisible forces that are constantly shaping our world chemical reactions. We're going to look at what they are, how chemists tell their stories, and why they are the engine behind, well, pretty much everything. From baking a cake to the stars burning in the night sky. You know the story, right? You slice up a perfectly good apple, you turn away for just a couple of minutes, and when you look back, it's already starting to turn brown. Or, hey, think about a shiny new nail you accidentally leave out in the rain. Before you know it, it's covered in this fleeky reddish rust. So what's the connection? Believe it or not, it's the exact same fundamental process at work. Yep, that's right. It is chemistry in action. These everyday changes are chemical reactions happening right before our very eyes. So in this explainer, we're going to pull back the curtain, decode what's actually going on at the molecular level, and learn the kind of cool, secret language that chemists use to describe it all. Okay, so let's start with the absolute basics. How do we even know when a chemical reaction is happening? What are the telltale signs we should be looking for that tell us a real chemical change is underway? At its very heart, a chemical reaction is really just a story of transformation. We start with our initial ingredients, which chemists call reactants. Then, through the reaction, those reactants totally rearrange their atoms to become brand new substances with completely different properties. And we call those new substances the products. Luckily for us, nature leaves behind plenty of clues. There are four main signs you can look for. You might see a change in state, like a liquid turning into a solid. You could see a change in color, just like our browning apple. You might see gas being created. Think of that awesome fizz when you drop an antacid tablet into water. And finally, you might feel a change in temperature, either because the reaction is releasing heat and getting warm, or absorbing it and getting cold. All right, so now we can spot a reaction. But how do we talk about it? How do we explain exactly what's going on? Well, chemists came up with a kind of universal shorthand, a language to tell the story of a reaction in a way that's super clear and efficient. So let's dive into this language of chemistry. And that language is the chemical equation. It's an incredibly powerful tool. You've got your reactants on the left, an arrow in the middle that basically means turns into, and your products on the right. The entire story of a transformation, all laid out in one single neat line. Now, here's where it gets really interesting because there is one rule, one huge rule you can never ever break. It's a fundamental law of the universe, the law of conservation of mass. All it means is that you can't just create matter out of thin air and you can't make it disappear. Every single atom you start with has to be there at the end. They just get shuffled around into new partnerships. It's like a cosmic head count. So to make sure our equations respect this universal law, we have to balance them. And it's basically a simple four-step puzzle. First, just write out the basic equation. Second, you do a little inventory, counting up all the atoms on both sides. Third, you add numbers called coefficients in front of the molecules to make the counts match up. And fourth, you just do one final double check to make sure everything's perfectly balanced. And this is a perfect example. Let's look at making water. On the left, in the unbalanced equation, you start with two oxygen atoms, but you end up with only one. Wait a minute, where did the other one go? It can't just vanish. So to fix it, we add coefficients, like you see on the right. Now with two hydrogen molecules and one oxygen molecule, we make two water molecules. Four hydrogens and two oxygens on both sides. See, the cosmic balance is restored. Okay, so now that we've got the language down, let's meet the different families of reactions. It turns out most reactions fall into just a few main categories, and each one has its own sort of personality. First up in our family album, we have the combination reaction. And just like its name sounds, this one is all about joining forces to build something bigger. In a combination reaction, it's pretty straightforward. Two or more simple things come together to form one single, more complex thing. The pattern is just A plus B gives you AB. It's a super common way that nature builds stuff. Next up, we've got the total opposite, the decomposition reaction. If combination is all about building up, well, decomposition is all about breaking down. You could even call it the breakup artist of the chemistry world. So here, we start with one big, complex compound, and it just breaks apart into two or more simpler bits and pieces. It's the perfect reverse of what we just saw. A single thing, AB, splits back into A and B. All right, now for the displacement reaction. This type is kind of like a chemical competition, where one element comes in and just muscles another one right out of the way. So the key word here is reactive. Some elements are just, well, they're more aggressive and eager to react than others. In this situation, a more reactive element, let's call it A, comes along and kicks out a less reactive element, B, from its compound and then takes its place. So A swoops in, bonds with C, and poor old B is left all by itself. And finally, we have the double displacement reaction. So if that last one was a single swap, this one's a full-on partner exchange. In a double displacement reaction, two compounds meet up, and they basically just trade partners. The positive part of the first compound pairs up with the negative part of the second one, and the other two pair up as well. Everybody finds a new partner, and you end up with two totally new compounds. It's like a chemical square dance. So why does all this matter? I mean, why bother learning these patterns? Because these reactions are not just stuck in some dusty old lab. They are happening all around us and even inside of us every single second of every single day. One of the most common and important types of reactions in our daily lives is oxidation. Now, in simple terms, this is usually when a substance teams up with oxygen. And remember our browning apple from the very beginning? That is a classic, perfect, everyday example of oxidation. And you see this everywhere. Take corrosion, for instance. That's just the slow motion process of metals breaking down as they react with oxygen. We see it all the time as the rusting of iron. And what about rancidity? That's what happens when the fats and oils in your food oxidize. It's what causes that stale, kind of nasty taste in old potato chips. So, the big takeaway here is that chemistry isn't just some abstract topic in a textbook. It is the engine that drives our world. From the way your body digests food for energy to the way a bike rusts in the rain, our entire existence is run by this constant, beautiful, and predictable dance of atoms. It's really amazing when you start to see it, isn't it? The battery that's powering the device you're watching this on, the photosynthesis happening in the leaves outside, the very act of you breathing. It is all chemistry. So I'll leave you with a question to think about. What other invisible chemical reactions are powering your world right now?